you went right to the task of trying to calculate the work done by individual forces. So you started breaking this up and thinking, okay, there's probably friction. Somebody even asked. There's obviously an applied force, there's gravity, there's normal force. Not all those forces are contributing to the work done, but probably a couple of them are. And yeah, I think that pushing force is doing work on the puck. And yes, I think friction is doing work on the puck. But it says constant speed, which means the net force is zero. So if you look at the second way of calculating work, which is the work done by the net force, if the net force equals zero, the net work has to be zero as well. But that's why I left the best one for last. I said the other way to calculate net work is to look at the change in kinetic energy. And if the object's velocity is not changing, kinetic energy is not changing either. So it was really just staring you in the face, but you got to really be paying attention. Net work changes the nature of what it is you need to do. Now, I'm not saying work wasn't done. Remember, I'm indicating that very clearly. Work can be done by multiple forces. But it looks to me like any amount of positive work is being followed by some negative work. Picked up on it, like it dawned on him. We got it. So, Daniel, it looks like you go to the gym. Do you go to the gym? A little bit? What do you bench? Like 220? 250?
My max is like 185.
So 220.
So
Yeah, 220. So Daniel's going to be going to the gym today. Today's chest and tri day, so he's definitely going to be doing some bench presses. And we'll say he's just going to do his warm-ups with 220. So 100 kilograms is about 220 pounds. So we'll get a couple of plates together, get in the heavy bar, and get ready to go. You know what a bench press is, right? Okay, so, well, it's clear. I mean, you are huge. Obviously, you know. So would you agree that on a standard bench press, you are going to probably lower the weight to your chest in a controlled manner, and then the power portion of your press will be the pushing up of the weights, and you'll push the weights upwards in a controlled manner, which I think suggests a constant velocity while the weight is leaving your chest. Would you guys agree? You're not trying to accelerate the weight upwards. You want a small acceleration to get it started and a small acceleration to make sure it stops. But during the process of pressing the weight upwards, it's supposed to be a controlled motion. Would you agree? You don't need to accelerate it. You're not throwing the dumbbell, right, or the barbell. You are just trying to lift the barbell. Everybody agree? All right, so let's get a measurement. Based on the length of Daniel's arm, he's going to be successful in getting us an extension of 50 centimeters. All right. How much work does Daniel do on the bar? I'll give you guys a minute. How much work does Daniel do on the bar? All right, who's person 14? Where are we? All right. Tell me how you calculate the amount of work Daniel did lifting the bar. I'm not going to let you off that easy. How about I just write out I'll write out our definition of work. Is that all right? So can we agree that the net force on the bar is zero? Because we're just going to try and lift it at a constant speed. Is that all right? So is it also reasonable that the force from Daniel will be upwards on the bar? But at the same time, there's another force acting on the bar, correct? That'd be what? Gravity. And I think we're all aware that gravity is still mg, 1,000 newtons. So how much force would Daniel have to apply to lift the bar at a constant speed? 1,000 newtons. Excellent. And how far is Daniel going to lift the bar? All right. And what is the angle between the lifting force and the displacement of the bar? 0 degrees. All right. So the work done by Daniel Looks to be about 500 joules of work. Pretty straightforward. Now, at the same time, there was another force doing work on the bar. How much work did gravity do on the bar? What's that? It did 500 joules, but it's negative. So if you look at the work done by gravity, and I wouldn't be super explicit about this, but I'm afraid that people aren't really paying attention. They're already looking forward to the good life, even though it's 4 days away. So let's be explicit here. We're talking about 1,000 newtons of force from gravity being done over the same 0.5 meters, but what is the angle between the weight of the bar and the displacement of the bar? That's right, 180. Right, the weight's downwards, but the displacement's upwards. So gravity did negative 500 joules of work. Right, so Daniel loses 500 because he's working against gravity. Now, as a brief aside, and nobody in first period had this answer, and I was very disappointed. But maybe you guys are better. You guys don't know what a joule is. You know, I mean, you have an idea, but let's try and frame this a little bit. How many joules are there in a calorie, or how many calories are there in a joule? You all passed chemistry. I'll tell you what, and I'm hoping you just knew it, and it's not something that's sitting on that iPad in front of you. Excellent. Now, what you said was 4,000, and I'm going to do 4,190 joules, but you're talking about a big C calorie, and that's okay with me, right? Which is also 1 little c calorie. Right? You guys do remember the difference? I hope so. That's right. That suggests that a joule is the smallest of the energy units that you guys know. If it takes 4.19 of them to be a little c calorie. So it suggests a single joule of energy is not that much energy at all. So keeping this in mind, and knowing that there's several boxes of world's finest in the room. So Oliver, why don't you give me what's the average calorie per bar? Bottom of the box. And yes, I know all the bars have a different amount. Just give me an average. 120. So let's say that before hitting the gym, Daniel consumes a world's finest so he can fuel up for the gym. How many reps would you have to do to work off your world's finest? We know it's 500 joules per rep. We have a choice here. You can either convert the joules to calories or convert the calories to joules, but it's 500 joules per rep, and we want to figure out how many reps you have to do. This is a conversion, and you guys learned how to do conversions. Come on, my straight A students. Let's work this out. All right, so do we have an idea of how many reps you'd have to do? 1,006 reps. So it's going to be a busy day at the gym today, isn't it? Working off that one. I guess lifting weights is not the calorie burning activity we all think it is, right? And it's true, it's not. I mean, that's not the intention of lifting weights. If you're attempting to burn calories, all of those devices are on a different side of the gym, aren't they? So the lifting of weights is about tearing muscle fiber and building it back stronger. If you want to burn calories, you're going to go to some kind of reciprocating device, correct? However, this is how the reciprocating device also does the math. So these reciprocating devices are just doing this. They are making the same kind of calculation. If your body weight's involved, they'll ask you to put your mass in there too. But oftentimes your body weight's not necessary. So like bicycles, recumbent bicycles, the treadmills and the ellipticals and the stair machines, they're all doing the same calculation. They're making a calculation of the force you're applying and what the distance you're applying it for in order for it to be able to calculate in real time how many calories you're burning. But I also want to be real clear. We're not making these numbers up. right? You would hate to have a calorie counter on your bench press machine. It might be a little demoralizing, even at benching 220, your normal warm-up. So I think we get the idea across here. But there's a little more that I want to bring to bear here. So one of the things I want to point out is this value here, doing work against gravity. It works out to be negative because gravity was trying to prevent the bar from going up the whole time. So you're working against this conservative force. Let's that a little bit, please. If you have just have a table here real quick just to get us started. So I have a table, and we're going to lift the box from the floor to the table. So I just take the box, lift it upwards, and just put it right here on the edge of the table. If the box has a mass of M, there's the work we do on the box, but there's also the work gravity did on the box. Based on just what we did a moment ago, would it be pretty clear the work that, say, you did lifting the box would just be mg times h to get the box up there, right? Following the same principle we just did. But the work done by gravity is going to be equal to negative mg times h. We're doing work against a gravitational force, right? It's the exact same calculation as a moment ago, just of stripping away the numbers. All good? Any question about that? Now, it's been long believed that the idea of lifting something against gravity is a means of storing energy. And the simple idea here is that just putting the box up on the table suggests that if you just give it a small push, the box will easily tumble to the floor, taking that potential energy, the energy of being lifted up and set on the table, and converting it into kinetic energy, right? The box is going to speed up all the way on its way to the ground. This idea of storing energy by lifting something against gravity is a very old idea. It was more formalized with Newtonian mechanics, but the idea of Newtonian mechanics and the storage of energy is that we call working against a conservative force the storage of potential energy. Potential energy it's going to be different than kinetic energy. Kinetic energy is something that an object by itself can have. This distinction is important, and I'm going to spend time making sure everybody takes a minute to write it down. Kinetic energy is something that an object by itself can have. If it's moving, the object has kinetic energy. But potential energy isn't like that. Potential energy is an interaction between two or more objects. The box doesn't have potential energy by itself. The box has potential energy because it's interacting with the Earth. In fact, we are spending some time separating the box from the Earth, a small amount. And the work we do separating the box from the Earth is stored in the Earth box system. Energies. There are lots of different kinds of potential energies, though. The two that we're going to talk about this year will be gravitational potential energy. And then later we'll talk about elastic potential energy. Part of the reasons why we study energy is because there's something interesting about the way potential energy works. Potential energy is stored because we're dealing with a conservative force. And the best part about dealing with a conservative forces are path independent, meaning it doesn't really matter the path the box takes to go from the ground to the table. When it gets to the table, the amount of potential energy it has is based solely on its absolute change in position. I'll say that again. It doesn't matter the path the box took to go from the ground to where it is on the table. The amount of potential energy it has is based on its absolute change in position. So we would say that all that matters is that the absolute change in position was the height of the table. Now, part of the reason that's important is because if I can't lift the box myself, and let's say the box is too heavy because I haven't been going to the gym enough, and I decide to leverage, say, a ramp, something I know that will reduce how much force it takes. Using the ramp, I could calculate the force necessary for the box to go up the ramp to get to the top of the table. And if I neglect friction for this argument, I'm applying less force on the box. If I want to lift the box along the ramp to get to the top of the table, well, I would be probably pushing with the amount of force equal to mg sine theta. Does that make sense? But I'd also have to take it from here all the way to here. Agreed? Which I would call, I don't know, let's call that just L for time being, for lack of a better term. So if I push directly up the ramp and the box goes up the ramp, I will be doing this much work getting the box up to the top of the table. You guys agree with that? Any question about that? Because here's where I'm going to kind of trip things up a bit. Sine theta equals h over L. Right? It's a triangle. That means this is mg h over L times L cosine 0. You see how the L's cancel out? It doesn't matter that I pushed along that entire length of the ramp. It's path independent. The amount of work done against gravity still comes out to be mgh. That's what I mean when I say it's path independent. It doesn't matter which path I take to get to the top of the table. The amount of work done in getting the box to the top of the table remains related to just the change in height of the box. Now, to put this more formally, we state that we're going to use delta U as an indication of the change in potential energy of an object. And it will be equal to minus the work done by a conservative force. This part's important because whenever you're doing work against a conservative force, the work's going to end up looking negative, but the amount of energy stored is positive. So when we lifted the box against gravity, the amount of work done by gravity was negative mgh. But the change in potential energy will be negative times negative mgh. So we will say that the change in potential energy is equal to mgh. This is how we will define gravitational potential energy. Often for a while you'll see me write it as mg delta h. I'm going to come to that too. Now, we don't have many definitions so far in this chapter, but one of the ones that I want to make clear is that we have two forms of energy right now. Kinetic energy, which has to do with something an object has, and potential energy, which is something that the object has because of its relationship with the Earth. These two forms of energy are probably going to last us through most of the semester. Although we will talk about elastic potential energy. To understand elastic potential energy requires, a little bit of calculus. So we'll get to elastic potential energy, and we're going to do it probably probably tomorrow. But one of the things that I want to be clear about is you may not understand where the derivation comes from when we talk about elastic potential energy. But here's one of the reasons why we study potential energy, or one of the more important reasons. Like I said, it's path independent. In a couple of days, Busch Gardens for Physics Day. And you might decide to ride a standard chain lift roller coaster. I don't know what your favorite is, but I like Montu. But I've still yet to ride Iron Gwazi, so every time I finally get a chance to go into the park because I'm dealing with some problem, Iron Gwazi's usually got a nice long line. So if you've ever ridden a chain lift roller coaster, and how many of you have? I assume it's most of you. It's only 3 or 4 of you have ridden a chain lift roller coaster? That's sad. Oh, now you're all putting your hands up. Yes, please. Let's actually answer the question. A chain lift roller coaster is exactly that. There's a massive chain at the beginning of the roller coaster that spans the lift hill. For lack of wanting to draw too much, we'll just draw one car. The chain lift has usually a stopper on one end. There's usually multiple stoppers, but there'll be one stopper on one end. The cars are lifted because the chain applies the force to the cars. The initial amount of work done is the work done lifting the cars up to the top of the first hill. To be frank, this is the most dangerous part of the actual roller coaster, because if this breaks, the chain goes backwards into the loading house, and that's caused tons of accidents in the past, which is why you hear that noise as the roller coaster goes up, that constant dink, 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 dink all the way up. You want to hear that noise. That noise isn't accidental. That noise is the actual emergency brakes that are constantly being locked into position to make sure if the chain breaks, you don't go backwards into the loading house and cause an accident. It also locks the cars on the track so that you can exit the ride vehicles. That's why that's the only part of the roller coaster where there's actually stairs next to the roller coaster tracks. Once you make it up to the top, it's all gravity from here. And from this point forward, you're probably in the safer part of the ride. Unless, of course, the ride itself has some kind of catastrophic failure. That does happen from time to time. But let's assume that we have no catastrophic failure. It doesn't matter how you get there. The amount of energy you have is going to be related to age. So at this moment, we have changed the potential energy of the roller coaster cars to give them a certain amount of potential energy. And yeah, it is related to how many people are on the car because mass is a part of this. Now, the other part of this, the part that's important, is that once you're up there, gravity does work on you to bring you back down. But that work is positive because you're being pulled downwards. But it's work done by an unbalanced force. So there will be net work done on your way down, causing a change in your kinetic energy, because this net work is done by an unbalanced force. Your velocity is changing. The best part about this is that work is being done exclusively by gravity. And again, path independent, which means this work done will be equivalent to how much potential energy you have. Meaning when you make it to the bottom, your change in potential energy will equal your change in kinetic energy. This is a statement of conservation of energy. And is a seminal idea in physics, that the energy of a system remains unchanged unless acted on by an external force. So as long as the only forces acting in our system are the internal forces due to gravity, the total energy of the system stays the same. In this case, we would be able to say the potential energy final minus the potential energy initial will have to equal the kinetic energy final minus the kinetic energy initial. Now, if you look closely at this and you bring everything to one side, that's going to be positive. So what I'm saying is I want to bring this kinetic energy to the other side to make it positive, and this potential energy to the other side to make it positive. I'll get what am I doing wrong here? Let me just back up and start here. I'm making a mistake that I don't want to make in front of you. The change in potential energy of the cars will equal the change in kinetic energy of the cars. That is the statement of conservation of energy. The thing that's important here is that the cars are losing potential energy as they fall downwards towards the bottom of the track. But they're gaining kinetic energy as they get closer to the bottom of the track. What this means is there's an exchange of potential energy and kinetic energy. Now, in a real system, that's not going to be exactly true. There's an external force acting on the system. That external force is actually two: air resistance and friction. These are constantly bleeding energy away from the system. But if there are no external forces, the entire amount of potential energy that we have at the top of the track will be converted into kinetic energy at the bottom of the track. But this is a constant exchange of energy. So for the time being, if we ignore external forces, you can figure out how fast the cars are going by just knowing how high they are above the ground. At any point in the ride, if we take a look at what's happening as the cars move along the track, they're going to have a combination of both potential energy and kinetic energy. If you're on a roller coaster, you understand that the cars are constantly going upwards and downwards through the track. The higher they are, the more that energy is being converted back into potential energy. The lower they are, the more that energy is in the form of kinetic energy. So you can probably assume that they're going the fastest here. They're going the slowest as they get back up to the original height. And they're doing something in the middle when they're in the middle of the track. But there's a constant exchange of kinetic energy for potential energy and potential energy for kinetic energy until the end of the ride. What happens at the end of the ride? They apply the brakes. The brakes are just there to do work on the cars and take away the energy. For the most part, they convert all the energy the cars have into heat. They use mostly friction brakes for most of these kinds of roller coasters, which just clamp onto little flaps on the sides of the roller coaster cars to stop them. And it's at that point that you'll usually see little embedded wheels in the track to push the cars around to get them back to the loading house. Now, everybody ever heard of the Matterhorn? Matterhorn is an old roller coaster at Disneyland. It's one of the oldest rides at the park. In fact, coasters that shoot riders into the rides, they wanted to use the lift hill because it's cheaper and it's generally more durable and more reliable. What they did is they happen to have, in Six Flags, areas with hills. So they built a roller coaster to the maximum height of the grade of the top of a hill so that their downward portion could go further downward than the chain lift lifted them upwards. It was to allow for a higher maximum height to get around the rules. Now, this question I'm about to ask isn't accidental or trivial. When we talk about how much energy we have due to gravitational potential energy, we state that the gravitational potential energy is equal to mgh. But I kind of want to change that to write it a little bit like this. When we're talking about how much potential energy something has, do the rail cars have potential energy because they were lifted from the top of the hill? Or should their potential energy be based on, say, a position down here at the bottom of the hill? Potential energy isn't a finite value. It's a relative value. I say relative because it's not based necessarily on the work done getting the cars to the top of the hill. It's based on their potential to fall. So when we try to calculate how much energy the cars have, the chain lift did this much work based on this height. But if I want to calculate how fast the cars are going, I probably want to base it on how far they have to fall to get to the bottom of the hill. This question is about reference. What is your reference level? When you're trying to calculate potential energy, you will often have to consider what is the reference level. What is the potential for the object to fall? When you look at the stuff on my desk, does the stuff on my desk have potential energy? I don't know. My iPad's not going to fall off my desk. I have it clearly in the middle of the table. But even if it does fall, is it going to fall to the floor? That's one potential energy, but I lifted it from the first floor to bring it up here. So there was work done getting it all the way to the table where it is now. But when I try to calculate potential energy, that's tricky. The total amount of potential energy is always related to a reference level. And that reference level is arbitrarily chosen. So when you're asking how much potential energy does something have, you should strongly consider, well, what's its potential to fall? that distance makes for the better amount of potential energy because it refers to what the object could do as opposed to what it's unlikely to do. So if I asked how much potential energy my iPad had,